One of the things I like to do when we're in the home stretch before the AP exam is take some time to go through the formula sheet to remind you of what model each formula goes with and what are some of the diagrams that we tend to use with that model. Now, in this video, I'm only going to go through the mechanics section of the formula sheet because that's the only section you're going to need for the 2020 AP exam. I also want to remind you that on the right side of your formula sheet, you have this list of what each variable represents. So if you're doing a problem that talks about momentum, and you, for the life of you, cannot remember what letter we use for momentum, look at this list. That's what it's there for. So with that, let's start working through the actual formulas. So these first three, we didn't really emphasize. These fall under the constant acceleration of a particle model, or CAPM. Rather than really pushing these equations, we focused a lot on velocity versus time graphs. And we were able to get all the formulas that we needed from those VT graphs. If you remember that the slope of a velocity time graph is acceleration, and you remember that the area of a velocity time graph is distance, and then you sketch a good graph, you take the time to annotate it, you're going to be able to get all three of these equations, plus a bunch more. That said, you can use these equations and you will get exactly the same answers. In fact, again, these equations are ones that can actually come from those velocity versus time graphs. So those are just two different ways to approach the same math. These next two were part of the force on a particle model, or FPM. Whoops, I did my P first. FPM. The two big diagrams that we really made a lot of use of were the FBD, not FBV, and the vector addition diagram, or the VAD. So the first step was always to figure out what are the interactions that a particle has going on. Then you figure out which direction each of those interactions, so each of those forces are acting, and you draw your free body diagram. Once you've got your free body diagram, you rearrange those arrows to make your vector addition diagram. So instead of drawing them all starting from that dot, you draw them tip to tail. And then any leftover bit is your net force. And then as a reminder, for this friction equation, this less than or equal to is just there because friction is only ever as big as it needs to be. So if you push something very, very gently, the force of friction is going to be just big enough to balance your push. But if you push with a force equal to or greater than that maximum force of friction, that friction is going to cap out and it's going to level off. This next equation, this AC equals V squared over R, this we did very recently as part of the central net force model. And once again, that free body diagram is key. Going back to what are the forces acting on an object, what are the interactions? And keeping in mind, there's only going to be a net force toward the center of the circular path when this equation applies. While it often feels like when you're going in a circle that there's something pushing you out towards the edge of that circle, there's not actually an interaction going on that's pushing you that direction. So that net force is always just towards the center of the circle. These next two, P equals M times V, and delta P equals FT. These are both part of the momentum transfer model. There's two major diagrams we made a lot of use of. We did a lot with SOS diagrams, where you have a sketch, then you have an interaction diagram, and then you have a sketch of the final situation as a way to keep track of changes that are happening. And going back to that idea that your initial momentum, so the total of all the momentum at the start, plus any interaction in the middle, so any impulse that was applied, equals the final momentum. And then impulse, that is force times time, or change in momentum. So impulse can refer to either side of this equation. And then the other diagram that we made some use of with momentum transfer model was momentum time graphs, where the slope of a momentum time graph is the force. The area we didn't deal with, but we did find that the area of a force time graph is the change in momentum. And so we did also do some force time graphs. And as a reminder, you can use this equation sheet to reason out those key relationships from graphs. Typically, when you have things that you multiply together, that could be describing the area of a graph. So if you have a force versus time graph, if it's a constant force, that area is a nice rectangle, so you just multiply force and time. That gives you the change in momentum. So that tells us that no matter what shape the force time graph has, its area is change in momentum. Similarly, I can see from this equation that if I were to divide momentum by time, I would get the force. So that tells me if I put those two things I'm dividing on the axes of my graph, I will get the force. All right. So then these three are part of the energy transfer model, or ETM. And with these three, with that energy transfer model, our big diagram were LOL diagrams. So being able to show the energy bar chart for the starting situation, showing the system in the place of that O, and then that second L is your final bar chart. Now scrolling down a bit, we have two equations that we did at the beginning of this trimester. And these are for the angular motion model. And again, just like those CAPM equations could come from the formula sheet, or they could come from VT graphs, these you can get from the formula sheet, or you can get from graphs. And the biggest one is going to be angular velocity versus time. And just like how the slope of a VT graph is acceleration, the slope of an omega t graph is angular acceleration. And just like the area of a VT graph is distance traveled, the area of a omega time graph is the angular distance traveled. This next equation is one you are not going to have to worry about. This is doesn't tend to show up on the AP1 exam, and it's used for a transition between simple harmonic motion and waves. And since waves don't show up on the exam this year, we don't have to worry about it. Now, next up, we have two more that are related to angular motion, but these go in that force on an extended body model. So we have the Newton's second law for rotation, and then we have that definition of torque. And the big diagram that you need when you're using this model is the extended FBD. So where instead of shrinking the object down to a point, you keep its full length and you show where those forces are applied, not just that they're there. These next two, we've also put under FEBM, force on an extended body, but they are dealing with angular momentum. And so these are the angular version of the momentum equations from further up. And just like we used SOS diagrams, we can use SOS diagrams for these. And just like we had momentum time graphs, now we can have angular momentum time. And we can have, instead of force time graphs, we can have torque versus time graphs. And we're going to see some really similar relationships, where the area of a torque versus time graph gives you the change in angular momentum, and the slope of an angular momentum versus time graph gives you torque. This equation we tend not to do a whole lot with, but this is essentially an addition to the energy transfer model. It is adding angular or rotational kinetic energy, and so that is something that just gets added to LOL diagrams. Next up, we have one that goes back to FPM above. This is something that can show up on your FBDs, on your vector addition diagrams. This is the formula for spring force. Then we also have spring energy, which is something that's going to show up in energy transfer models. So if you do energy bar charts, this is one of the types of energy you can have. Though as a reminder, potential energy only shows up when both the objects involved in that interaction are part of your system. And so if you don't include the spring in your system, you can't have that spring potential energy in here. And then really similarly, we have gravity or gravitational potential energy up here. And again, you need to have Earth in your system in order to include gravitational potential energy. Now, I did kind of skip over this equation right here. This is one that we didn't really use. I haven't seen it come up on the AP exam in the past, but this is a formula for density. That funny looking P, it's a Greek letter rho. That is the symbol that physicists tend to use for density. And so it's just showing us density is mass divided by volume. All right. Next up, we have these three equations. These three are all part of the oscillating particle model, which that is fair game for this year's AP exam. So this is for, we have the formula for the period of a spring, and then we have the formula for the period of a pendulum. And so you pick whichever one best fits the situation. And then this lets you relate period and frequency. This also works for angular motion. And so this first equation could also go under the angular motion model. All right, that leaves us with three equations left. This right here, this is the formula for universal gravitation. We used this as part of the central net force model because the main place where this equation comes up is when you have two planets or a planet and a satellite and you're trying to describe the force of gravity that causes something to stay in orbit. So when you have these two massive things, when you've got a significant distance, when you're dealing with the force of gravity for something besides everyday kind of object near the surface of the Earth. And so since orbits are pretty close to a nice circle, we ended up just doing that universal gravitation as part of the central net force model. And it's going to be extremely rare for you to see this universal gravitation in a different context. Then we have the equation for finding the force of gravity near the surface of the Earth on fairly everyday objects. And so we used this as part of that force on a particle model. This little g, that's that number that's always 10 newtons per kilogram. And you are given the value on the other side of the formula sheet. Now this last equation, we didn't really talk about this here. This one is, so it's UG, gravitational potential energy. But this is what you'd use to find gravitational potential energy in the same contexts where you would use that universal gravitation equation. So where you have massive objects and when they're far away from the surface of the Earth. Aside from that, it gives you the gravitational potential energy. Whoops. If we scroll back up and we look at that other equation, because it's got that little g in there, that means we're making the assumption that you're near the surface of the Earth and that you're not dealing with anything too huge for your object besides the Earth. So anytime that those conditions don't apply, that's when you would use this last equation to get your gravitational potential energy instead of the one that we normally used this year.